Hello, I hope you can hear me.
Yes, sir. Yes, sir.
Okay, fine. Let me just start sharing the screen and then we can continue start.
Sir, we have an inaugural event where there's a few lines that someone has to speak. After that, you can start, sir.
Okay, please go ahead.
Thank you, sir.
Good evening, everyone. We Team Nakshatra are here with the maiden edition of our event, AstroChamp'. First of all, I would like to welcome Dr.
A
Manojendu Choudhury
few
and all others present here
lines
on
that
behalf
someone
of
has
Team
to speak.
Nakshatra
After
to
that,
this
you can
inaugural
start.
evening.
Okay, please go ahead.
The sky and horizon and its happenings have always garnered the interest of
Thank you,
humans,
sir.
serving as a peephole to an infinite universe lying beyond the surface, compelling us to explore it. Theories regarding its workings have been
Good
there
evening,
forever,
everyone. We
whether
Team
it be through
Nakshatra are here with the
observations by
maiden
naked
edition of our
eyes
event,
in historical
AstroChamp'.
eras,
First
or
of
with the
all, I
use
would
of
like to
highly
welcome
advanced
Dr.
technical
Manojendu
equipments and
Choudhury and all others
telescopes
present
or
here on
theoretical
behalf of Team
calculations.
Nakshatra to this inaugural evening.
Okay,
Never
please
always
go
the
ahead.
sky and horizon and its happenings have always garnered
International
the interest of
Astronomy Day,
humans,
occurring twice a year,
serving
is
as
an
a
occasion
peephole
for
to
us,
an infinite
astronomy
universe lying
enthusiasts,
beyond the
to celebrate
surface,
and devote a day
compelling
to
us to
expand our
explore it.
knowledge in
Theories
the field of
regarding its
astronomy
workings
and
have
to
been
share
there
a part of our
forever,
knowledge about
whether
the
it be
mysterious
through
space we have
observations
witnessed.
by
In
naked eye.
1973, Dirk Berger, the president of the Astronomical Association of Northern California, first started this event with the intent to set up telescopes in busy urban locations so that passers-by could enjoy views of the heavens. This marked the beginning of yearly celebration of Astronomy Day. Originally, Astronomy Day occurred on a Saturday between mid-April and mid-May and was scheduled to occur close to the first quarter moon. However, in 2007, an autumn edition of the Astronomy Day was added too.
Team Nakshatra and the Astronomy Society of IIT Bhubaneswar has always been active and excited to learn and to share exciting and surprising discoveries of the universe. We strongly believe astronomy to be a wonderful experience and do our part in enabling more people to understand and enjoy this experience with us. We strive to keep updated with developments in astronomy via Instagram and Facebook handles, along with some fun and engaging quizzes and published bi-monthly magazine called Relativity.
This Astronomy Day, we are here with our first edition of AstroChamp'. AstroChamp' is an event that celebrates, nurtures, and promotes curiosity about outer space and the universe. It has competitions, guest talks, and a group of like-minded people who want to find answers to the secrets of cosmos. Along with informative and interesting guest talks, workshops, and webinars, there are various competitions in all fields like literary, art, designing, photography, quiz, and many more. You can register and take part in our events through our website. Hope you are all hope and active participation from all of you. Show your support, enjoy, and gain from these events. So, without any further ado, let's begin AstroChamp, where astronomy attains singularity.
So our wait is finally over. Today we have Dr. Manojendu Choudhury here with us. So Dr. Manojendu Choudhury is a high-energy astronomer and an educationist who has been associated with numerous institutes like IUCAA, UM-DAE, CEBS and TIFR in the past. He has deep knowledge in astronomy and astrophysics, and he has been the team leader of the Indian team to the International Olympiad on Astronomy and Astrophysics, as well as the International Astronomy Olympiad multiple times. He has the experience of teaching students from high school to the Ph.D. graduate course in subjects ranging from physics and applied mathematics to computation and management. Today, Team Nakshatra has arranged a very interesting session with him, where he provides us with a deep insight about the topic. Questions will be taken at the end of the lecture, and to ask your questions, you will have to fill up the Google form mentioned in the email. Now I request Dr. Manojendu Choudhury to start the lecture.
Okay, thank you everyone for this kind words. And it is indeed my pleasure to associate myself with this event that you are hosting. And as I understand, this is the first time you're doing it. I hope this marks the beginning of a long journey where students discover the joys of astronomy and astrophysics. And as it happens that I was asked to, give this talk on this particular topic of black holes. So black holes is the term itself is very, very attractive, I'll say, because it gives you a hint of mystery, something hidden in the dark that you can't see. It's like, Alice in Wonderland, falling through the hole and discovering new vistas, new worlds. So it kind of the terminology of black hole has gone a long way in popularizing this concept of astronomy, rather astrophysics. And this is actually a very, very vast topic. From very deep mathematical, theoretical insight and investigation to the most cutting edge telescopes and observation techniques. This topic cannot be covered in one lecture. Let me be very frank. So what I will do instead is basically it will be a kind of a teaser section where I will introduce you to many other topics. I mean, many topics, not other topics, many related topics, obviously, which perhaps you can later explore on your own, because this does require very intensive understanding and imagination to visualize what is said and what is done and what people are doing. And believe me, this is not a new journey. It has taken centuries. So let's see where we stand when it comes under understanding of black holes and how did we really start. Before the start, I'll say although black hole has been very intriguing, when we were in school in 1980s, then also we heard of the term black hole and everything and all the related concept in relativity and all. But it has taken time for the scientific community to accept this concept and the existence of this particular class of objects as something real, that is something scientifically accepted by the community. So there are obviously certain landmarks which has caused this shift in the paradigm and also shift in the approach of people. Mind you, Roger Penrose has been working on these sources since 1960s, late 50s and 60s. People have been working on observing black hole binaries till from 60s and 70s. But today we find ourselves in a situation where we are actually appreciating these objects and the theoretical paradigm and all the efforts to observe them because of these certain landmarks that we have crossed in the recent past. And the latest of it is the direct imaging of the supermassive black hole M87 by the Event Horizon Telescope collaboration. Now, I think most of you, if not all of you, have seen this particular image. This had been one of the most circulated images that we have circulated in the domain of science and science outreach and popularization and reaching out to the general media of news and other social media. Okay. So here what we see is an image which appears to be orange in color, and there's something dark which is supposed to be the black hole inside. And I remember distinctly that one student from high school, or maybe I think he's from, class 7th or 8th standard, in one of the outreach programs in IUCAA, he came to me and asked me, why is the color of the image orange? What does it signify? And I think This is a question many of us wanted to ask but didn't ask. And then we slowly got used to the fact that all the images that we were seeing around was orange. So, this must be an orange colored black hole. Okay. Of course, the black hole doesn't have any color. It is in the center. It doesn't emit light, but the environment is orange in color. Now, the first and foremost thing that all of us need to appreciate is that this is a false color image. Please understand that most of the scientific images that we take are actually false colored images. We have the whole electromagnetic spectrum, of which a small window is the optical window to which our eyes are sensitive. Lower energy moves towards infrared, then far infrared, then millimeter waves, and then we move to the radio band, which is huge. And on the higher side, we move towards ultraviolet, then X-rays, then gamma rays, then very high energy gamma rays, very high energy gamma rays. So please appreciate that this particular image that we see is actually a radio image. Okay, this is not an optical image at all. Simply because this image requires very, very high precision observation. The size of the object that we see in the sky is extremely small. So as you can see out here, these are all these telescopes out here which have combined to create this image. Effectively, what happens, you take this whole area down here that you can see. This is like a huge lens. And we are combining small parts of the lens. Of course, this lens has huge gaps. Imagine a huge lens with many gaps, and there are small portions where you have the mirror. In place of the mirror, we have the radio dish antenna working at the particular frequency. Okay, I will leave it to you to find out what is the frequency of this particular observation. It is readily available. If you just Google it, one keystroke search will give you. So but my request is that always understand that the color of the image that you see is not necessarily the actual color. Here it is radio. And why it is radio? Because when we are combining data from all these telescopes, we have to do something called interferometry. That is, we are adding these images in phase. If you remember your school level physics, wave optics, interference of wave. So this is nothing but we are measuring the wave at these different telescopes and adding them in phase. So that is interferometry. And this is best done when your wavelength is long. So we have the technology for very good interferometry at the radio wavelength. As we move higher in the energy spectrum or the frequency spectrum, that is move from radio to infrared, our ability to use interferometry decreases, and beyond that we are still experimenting how to do it. Okay, but this image has had tremendous effect on the whole worldview of not just scientists but general public. And so this is a landmark which has caused a shift in our worldview. Prior to this, only few years prior to this, another event happened. Rather, I'll say another landmark was crossed when we measured the gravitational waves for the first time. This was another observable attribute of the general theory of relativity. And we didn't really have a direct proof of many aspects of relativity other than Mercalli's perihelion and gravitational lensing. But this particular observation is a landmark because people have been trying desperately to observe the gravitational waves for last 70 years or something. Post Second World War, we have had generations of physicists dedicating their lives to measure this, but they were unable to measure simply because these signals are so weak in nature that any detector that you build is overwhelmed by the noise all around, including the thermal vibration of the ground. If a truck goes by, it creates havoc in the vibration of the ground. So if we just look at the y-axis out here, what we are measuring is a wave pattern, a chirp, okay? And here the strain is 10 raised to minus 21, okay? That means the delta L, the change in length I'm measuring is 10 raised to minus 21 upon 1. If I have an interferometer of length 1 meter, I will be measuring a change in length 10 raised to minus 21. If I have an interferometer of the length of 1 kilometers, I'll be needing to measure a length of 10 raised to minus 18. Can you imagine that? The size of the nucleus of the atom is of the order of 10 raised to minus 15 meters. So that gives you an estimate of the precision that we need to measure these gravitational waves. And it is amazing that we have been able to cancel out the noise and have been successful in measuring it. Okay, so I would really request all of you to, when you have spare time or whatever, go and read about just the engineering aspect of measuring a gravitational wave. You can imagine the extent of vacuum that is needed to be created. Because if you don't have that level of vacuum, the detectors will be overwhelmed by the noise. What are the so many different noises that we have to cancel out? Okay, it's an engineering feat that has been achieved. Then another one small thing that I want to mention here is the nature of gravitational wave and how is it different from the electromagnetic wave, which is very common for us actually, because we can see the light. We use radio all the time when we are using our mobile telephones. Okay, we use X-rays. Anybody who has had a fracture has used X-ray for diagnostics. Okay, so we use electromagnetic rays, that is light, all the time. Now, the dominant form of radiation of electromagnetic wave is a dipole radiation. That is, you have a dipole of a plus and a minus sign separated, and they vibrate. Here, when it comes to gravitational waves, we have only one charge, you can say, of mass. Electric charges, there are two charges, plus and minus. But for mass, we have only one charge. There is no negative mass, mind you. So the nature of the gravitational wave is different from the electromagnetic wave. And the lowest polarization that we can see is the quadrupole polarization. The dipole polarization we cannot measure, we cannot see. Okay, so this is the nature of the vibration that we measure, the lowest polarity that we. that we can measure. So I think if you're interested in fundamental physics, this is something also very, very interesting that we should see and talk, discuss sometime. Now, the direct observation of black holes established that, okay, we have a direct observation. Then the gravitational waves also had previously established that, okay, the attributes predicted by the theory of general relativity are proved to be correct. So the consequences of the theory, and one such consequence is the existence of black holes, should also be correct. At the same time, rather before that, if you go back 10 to 20 years, then something extraordinary happened in the field of observational astronomy. Again, this is an engineering feat where we were able to map the motion of stars around our galactic center. So this is an image of the galactic center. Mind you, this is also an infrared image. This is a false color image and infrared image. Sorry, this is a radio image. I'm very sorry. This is not an infrared image. This is another radio image. Okay, where it's about a meter wavelength. Okay. And you can see all these objects that we have around. Okay. Look at the scale here. This distance is actually of the order of half a degree. Okay. Which corresponds to a distance of around 240 light years. So this length is 240 light years, say from here to here, which is again corresponding to another unit called 75 parsec. If you are not comfortable with parsec, forget it. You can have an idea and estimate what a light year is. It's around 240 light years here. Okay. So imagine that we are here. Look at this figure on the left. This is a schematic of our Milky Way galaxy, the different arms. We are located here. This is the center of the galaxy. And this galaxy, this galactic center, is about 26,000 light years distance from us. Okay. And we are measuring here, this scale is about 240 light years. So you can understand what scale are we talking about, what is the accuracy that we need to measure these objects. 240 upon 26,000, and 240, this huge distance is 240. Okay. In fact, when we had to measure the actual path, it was very, very difficult because it was done in optical. And this measurement, which was done in optical and radio, okay, this is an X-ray image, how the galactic center looks like. You can see this is the enlarged part here. So when stars motion were observed around this center, what was realized is that we have a supermassive black hole here, a very huge mass in a very, very small region. Okay, so this observation, this series of observation took about 16 years. That is the shortest period of one of the closest stars near this galactic center. Okay, so this was also a dynamic proof of the existence of a compact object of the dimensions of a black hole, of a supermassive black hole. So you can say in the last 20 odd years, these were the main landmarks why black hole has been now kind of accepted in the scientific community, and people have been awarded Nobel Prize for these. Okay, so now that we have admitted this particular entity into the family of well-established entities, cosmological entities, cosmic objects, then let's go back in time and see where did the idea of such objects come from and how did our understanding evolve. Okay, so let's go to 1783. That is about, about 100 years after Newton gave his laws, and 1796. Okay, so we have John Michell out here, who both Michell and Laplace were actually people ahead of their generations. Laplace, I think, engineers, either you have already heard of him or you will definitely hear of him, because he has made a lot of contributions which are utilized in all of your engineering branches. Okay, Laplace transform, I think we all of us have heard of it or we will hear of it and apply it somewhere, sometime or the other. But these people in those days, they were actually polymath. They were polyglot, not even polymath. They were polyglots. Okay, their expertise was not so narrow. And John Michell was another such a person. He was a priest and he was an astronomer. He was a physicist, mathematician, and he was the father of the science of seismology. He gave the postulate that, seismic waves travel inside the earth. And he gave the idea, the mathematical concept of how it does and how it causes earthquakes, and also, how it has transformed the earth, because of his idea that nowadays we have an understanding of how earth has evolved over last billions of years. In addition to understanding what is happening inside the earth, he also looked outside the earth into the universe, and he came up with this idea of dark star, which a decade later was independently arrived to by Laplace also. Okay, before we understand what he said, let's just recall what we all have known since our school physics is the concept of escape velocity, right? So escape velocity says that if we have velocity beyond a certain threshold, then that object will no longer remain confined in the gravity of the host. So if we have a Superman who kicks the football with a speed above the escape velocity for the Earth, the ball will escape into the space. Now here, please understand one thing very, very carefully. When we talk of escape velocity, we are talking about one impact, one time instantaneous transformation of energy into the object which is escaping. If you look at our rockets and if you measure the speed at which they move, I am sure you can go through the videos that ISRO releases of their rockets, and you go through their launch videos, when the rockets are being launched, you will be told at how many seconds what height has been achieved. Then if you go through that and you just measure an offhand, rough calculation of what is the speed of the rocket, you will realize that the speed is far less than the escape velocity. Now, this is actually a very simple thing, but at the same time, a fact that most of us miss out. That the fact is that escape velocity assumes there is no other energy transfer happening. The only energy is the kinetic energy of the particle and the gravitational potential of the host of the object. But when it comes to rocket, it is not just that. We have the energy from the engine of the rocket. And that is why rockets are able to escape, because we have a sustained source of energy, and this sustained engine action is what enables rockets to escape despite having a speed less than escape velocity. But let's come out of the rocket sphere again. Let's understand what Mitchell and Laplace said. They said they came up with their own calculations. Okay. And their calculation was that for Mitchell, the calculation was, if I have a star which has a size 500 times the size of the sun, with a density of that of the sun, then the escape velocity of that object will be the speed of light. And in that case, we will not be able to see that object because light will not be able to escape. Laplace came with a slightly different calculation. He took a more dense object. He took a star which was about 4 times as dense as the sun, which happens to be the density of the Earth. And he came up with the size of a 250 solar radius. And the consequence is again existence of a compact object from which light cannot escape. Mind you, this was the end of the 18th century. And we were far away from even imagining that such objects can exist or they can be observed. Of course, John Mitchell had his ideas how these objects can be observed, but he was far too ahead of his time. And it is today, rather you can say in the second half of the 20th century, when high energy astronomy, X-ray astronomy developed, we were able to see how John Mitchell was right. But yeah, nobody paid much attention to these numbers at that time. The next, okay, before that, let's understand one thing, one very crucial aspect. This is about Newtonian dynamics. When we have two objects, okay, say the sun and the earth, or the earth and the satellite of the earth, okay, then any small object which is falling on the massive object, say how did earth get captured by the sun? Or if, let's say, hypothetically, we have the sun and from a large distance an object is falling, will it be captured by the sun, or what will happen to it? Okay, so now here you can see this dotted line at the bottom. Okay, this dotted line gives you the gravitational potential. Okay, as long as the object that is coming has an energy more than this gravitational potential at a particular distance r, it will be falling in to r equal to 0. It can't go out. Okay, but mind you, this is only the gravitational potential. We have something called an effective potential which exists because of the angular momentum. Now, gravitational potential for attractive bodies is negative, so it is always below 0. But angular momentum can at least be 0 or more. Okay, and this is the effective potential of the angular momentum. Okay, as a result, the sum of these two, I have this particular potential. Okay. So let's look at this particular potential. Here it is equal to 0. Now, any object which falls, if it is a bound object, that is its total energy is negative. That is the total kinetic energy plus the potential energy plus, okay, this total energy is 0. Then it will be less than 0. The total energy is less than 0, and say it is here, it will be bound in this region. It will move from a small value of r to a greater value of r, where r is the distance from the sun. Mind you, even if I have positive energy, that is a body which has kinetic energy, which overcomes the negative potential energy, even then it cannot reach r equal to 0, because this energy barrier. And what happens is that it reaches a minimum distance of approach and flies away in a hyperbolic path. Okay, so this is something which might be, you might have come across this particular potential well. This is the potential well of the planets, and this different value of radii gives us the elliptical orbits out here. As we go nearer and nearer to this equilibrium point, here exactly at this point, the lowest minima, the r doesn't change, and so it becomes a circular orbit. Okay, now why is this important? This is important because it shows that in the Newtonian dynamics, there is no object that can fall onto the compact object, which is a heavy mass at the bottom, at the center. Okay, so what it means is that a black hole cannot acquire any matter from the environment if we follow the Newtonian dynamics. Okay, so this is a very, very important thing that you should realize, that without the relativistic dynamics, we cannot have a theoretical framework of a black hole acquiring mass. Okay. Now, the next step that we should talk about is the general theory of relativity proposed by Albert Einstein, which you all know, in the year 1915. And now I think I should, I need to fasten up my speed a little bit. So I will just mention few things. Okay, these concepts actually require long lectures, long coursework for you to understand. But what you need to understand is, first and foremost, the Minkowski diagram, that an observer is here and we have the space and time combined together in one coordinate system. And any events which are causally related, when I say one cause affects the other, then some information has to pass. The information cannot pass faster than light, so it has to be within this light cone, because anything moving will move at a speed less than the speed of light. That is the postulate of special theory of relativity and also of general theory of relativity. Okay, and so if I have one event happening here, another event happening here, then they cannot be causally related. For any causal relation, for any information to pass through, it has to pass through in this cone. And mind you, this whole cone is existing in one particular instant. If I have to find a relation between object at this point and at this point, then I have to go back and transfer the cone here, the point of this cone here, apex of the cone here, and then see whether these two events fall within the cone or not. If I go to the future, then again I have to do the same transformation. Okay, so this is what you need to understand, that anything that moves within any two events which are within this cone are time-like events, and they can be causally related. One can cause the effect the other on the other by passing information, whereas these events, any event here and anywhere else in this space, they are not causally related, they are space-like events. Okay, so please understand one thing: time-like events and space-like events. Okay, these are space coordinates. In space coordinates, the characteristic is I can move back and forth in space, right? I can move forward, I can move back, I can move left, I can move right, I can jump up, I can fall down, I can do all kinds of back and forth motion in space. But the time axis moves in one direction. I cannot go back in time. So space-like coordinates, space have the property that you can move back and forth. The time-like coordinate have the property that you cannot move back and forth. And it is using this property that we define the metric of space-time continuum. Okay. The second thing that you need to get a hang of is, this is my field equation, Einstein's field equation. This looks pretty complicated. I will not derive it, definitely. I don't have the time. But what I want to emphasize is that this quantity, G mu nu, this gives you a space-time curvature. It's like a curvature in space. And this side, this T mu nu, is my energy momentum tensor. Okay, this gives me the dynamics or the motion of the particle in the curvature in space-time. Okay, and so in this one equation, our worldview was completely changed, where we realized that space and time are intricately related, and any energy or momentum, and as a consequence of energy, we can mention mass. The presence of any energy or mass or momentum causes a curvature in a space-time fabric. This is kind of a most common picture that you get, that this massive object creates the curvature, and any small object has no option but to follow this curvature. Okay, but actually this is a slightly misleading picture, because you have only one dimension of space and one dimension of time. Okay, we have to get a better picture. So this gives you kind of a picture that this is 3-dimension, how the curvature may look like. But what happens is that this is also slightly misleading, because this gives you a curvature in space. In reality, the curvature happens in the fabric of space-time. So here, if you look at this particular Minkowski diagram, this time and space, the curvature is created here. And visualizing this is the most important part in general theory of relativity. Now, when Einstein gave his theory, he didn't know that within 2 months, Carl Schwarzschild will give a solution, because he had given the theory, the equation. Solving an equation is a completely entirely different ball game. And Schwarzschild, a genius, he did that. He didn't survive long. He perished in the First World War. But he gave a solution where we are talking about a stationary spherically symmetric object. This is a gravitational potential of a point mass. This object is known as Flamm's object. Okay, this is not a gravitational potential, but it gives you the metric in Schwarzschild metric. It provides a visual depiction of the Schwarzschild metric. Mind you, this is not a gravitational potential, although the ideas are very similar, but this is not a gravitational potential. This is the Schwarzschild metric. Okay. Now here, this is a hyperbolic equation. What is important is that this is my space-like coordinate and this is my time-like coordinate. Okay. And I have the equation in the form of x squared minus y squared, which is an equation of a hyperbola, and this remains constant. And in relativity, this particular remains constant. So this is how we define the metric, that interval from dr and d theta and d phi, which define my space, minus this quantity of my time, this quantity will always remain constant. And if you explore it, this gives you all the concepts of time dilation and length contraction, and everything is preserved here. Now, please understand that this quantity 2gm by c squared, if I bring r here and c here, this becomes my escape velocity of light. Okay. And this particular quantity from the escape velocity of light, if I transform it and get the value of r, which is Schwarzschild radius, then you understand that rs, I write the same metric in terms of Schwarzschild radius, and immediately we'll see that when this quantity, mind you, this is 1 upon this whole bracket out here. So rs upon r causes problem. It causes a singularity out here. I cannot do any calculation. And this was a problem which existed for a long time. And a huge amount of research went in understanding this particular issue. So first big step was taken by Robert Oppenheimer, and he understood that this particular quantity rs, which corresponds to the escape velocity of light at that particular distance, is actually a kind of a horizon, and information cannot come out of it. He was the first person to kind of decipher it when it comes to a spherically symmetric object. Okay. But people were not at all comfortable with this idea of a singularity, because this also has a singularity. This whole metric has a singularity at r equal to 0 also. Okay. So at r equal to 0, things diverge. So that becomes a singularity. So that is also something people were not at all comfortable with, including Einstein himself. Okay. And he was also not very comfortable with this idea of an event horizon coming up. Nevertheless, people worked, and John Kerr, he gave the one of the most intricate solution of the field equation when he considered the angular momentum to be non-zero. Similarly, there were other solutions called Reisner-Nordstrom solution, where they considered the charge to be non-zero. And then we have the most general Kerr-Newman solution, where we have angular momentum non-zero, charge non-zero, but spherical symmetry was preserved. Okay. And that was the situation when Roger Penrose enters the field, and he comes up with his solution, where he, along with Stephen Hawking, creates theorems called singularity theorems, and he comes up with the idea of trapped surfaces. Okay, what does trapped surface mean? Before we come to the trapped surface, there are few things that you should really understand. One is the concept of proper time. that is the time measured by an observer who is stationary and going across this axis, and a time measured by an observer who is moving in space, they are not the same. And if this guy is measuring an event, then what he measures is known as the proper time. Okay, whereas a stationary observer far away will measure a different time. Okay, and this time will be actually dilated. He will measure much more time, much longer time. That is what time dilation is. Okay, so what Roger Penrose came up with the idea was that this cone, which determines how my light comes out, because light can't come out faster than this. So any line which is drawn with this particular slope can't exist. So all my information will be along this. So light, if I flash light here, then it can only move inside this cone. And what Penrose showed is that as we move towards the black hole, the curvature in space-time ensures that my light cone is all turned inwards. That is, light gets trapped inside this surface called the event horizon. And this is irrespective of the spherical symmetry. Even if an object is not spherically symmetric, the light will remain in this cone, and whatever light the observer emits will move towards this singularity. Another aspect is that once you move to R less than RS, then what happens is that my space-like and time-like coordinates interchange the characteristic. So my space-like coordinates actually becomes unidirectional. And as my time progresses, I will move only towards the singularity. So my space-like coordinate becomes unidirectional. I cannot move back. Now, this is a very, very intriguing property, and it's very theoretical in nature. I will not delve any more time on this because I'm running short, but I will ask you to read about Penrose diagram, where he gives the whole concept of how a particular star can undergo the whole system of evolution, whole series of evolution, not system, whole series of evolution, and collapse into a black hole in finite time. In finite time, but an observer who is observing from outside, okay, will actually see dilated, just as you can see time dilation happening out here. When an object falls inside the event horizon, the time dilation seen by an observer at infinity becomes infinite. So these are some mind-boggling consequences of the whole theory, which requires some time. And I will request you to read about these. Let me now jump towards this gentleman, especially Amal Kumar Rai Choudhury, because it was based on his equation that Penrose and Hawkins were able to create or prove their theorems on singularity. And it was this theoretical paradigm which established the existence of black holes. And I may say that had Hawkins been alive today, he also would have got the Nobel Prize along with Roger Penrose. It is just that Nobel Prize is not awarded posthumously. So it is unfortunate that Stephen Hawking's name is not included in the list of Nobel Prize winners. But at least we have Roger Penrose out there. And we should not forget our own Amal Kumar Rai Choudhury. He was a great theoretician, And his work is seminal when it comes to establishing the Penrose-Hawkins theorems on singularity. Okay, now, since I don't have much time, I will just say that any star which goes through the whole evolution becomes a compact object after shedding its outer layers. The smaller stars, like the sun, become something called a white dwarf. The bigger stars becomes a neutron star, and bigger than that, they become black holes. Okay, so if a star has something like 1.5 solar mass, it will become a white dwarf. Up till from 1.5 to 3 solar mass, it will become a neutron star, and any star above 3 solar mass will become a black hole. Okay, now how do we observe the black hole? So what Mitchell had predicted in 1783 when he talked about his paper was that if you have a binary system and one star is his dark star and the other star is a normal star, then by measuring the dynamics of the other star, we can measure the existence of the black hole. It was actually a revolutionary idea, and binary systems have been measured. And what I have here at left is actually a very, very intriguing binary system. This is also, if you're interested, you should go through this Algol system, because it is a very, very confusing system, and it caused a lot of confusion about the evolution of stars until it was resolved, that how stars evolve differently when they're in binary systems, simply because of mass from one is accreted by the other. Now, this process of one star getting mass from the other is best seen in what we call the extra binary stars. This is the, one of the biggest accomplishments of the second half of 20th century, where extra astronomy established the existence of such extra binary compact systems, where one star is a compact star, either a neutron star or a black hole, which accretes matter from the companion star. And this gravitational wave out here, this gravitational potential out here, the gravitational well is so deep, the gravitational potential is so deep that matter that falls in loses that amount of energy, and that energy is emitted in terms of X-rays. Okay. Now, as it happened, the development of Penrose's theory and the development of extra astronomy happened together. At the same time, we also had the observation of quasars. Okay. Before we go to quasars, let me just show you this one particular slide. Here, this is my Sun Mercury length. Okay. Now, from here, this length, you can see that these are binary star systems and how compact they are. They have to be compact because Cygnus X1 has a binary period of few days. Okay. And you look at the compactness of these binary systems, where one star is a compact object, okay, accreting black holes, and the others are normal stars in evolved stage. Okay. And what happens is that as the compact object accretes the matter, the amount of energy lost, the amount of gravitational potential energy lost is so huge that it is emitted in X-rays. So if I have 1 gram of matter falling into a black hole, okay, then it will emit 10 raised to 20 Earths. Imagine 1 gram. And this is more efficient in getting energy than your nuclear burning. Okay. So accretion happens to be generating more energy per unit mass than your nuclear processes. And so if I have a object here which is getting matter from the environment, then depending on how near it is coming, I get high energy or low energy emission. Okay. So as you come very near this gravitational well, I get X-rays. Okay. Now, let's at the same time, let me just get here. This can be a stellar mass black hole with the mass of 5 to 10 solar mass, or it can be a supermassive black hole, which can be few thousand solar mass, or it can be a few million solar mass, or it can be a billion solar mass as well. Okay, and it is accreting matter from the environment. Okay, so now let's understand that when we have a supermassive black hole, it is actually at the center of the galaxy. And what John Mitchell and Laplace had predicted about dark stars, they can be actually realized more realistically by a very small size AGN or something, or an intermediate mass black hole. Okay. Now I will quickly run through the observation of our galactic center. So when we look at a galactic center, we have the region which is extremely bright. Okay. This is approximately the brightness of 200 full moons. Okay. When we are looking at it in the night sky. So if we are trying to observe these stars individually in that bright noise region, we need to have very, very sensitive observations. And the two observatories which has done this in the last 2 decades is one is the VLT and the other is the Keck Observatory. Okay. So this is the very large telescope, and the person who was the leader of this observation of our galactic center, Sagittarius A region, was Reinhard Genzel. And the person who led the Keck telescope for this observation was Andrea Ghez. Okay, and it was their pioneering observation which has resulted in the dynamical proof of the existence of a very compact massive object, which is our black hole, supermassive black hole at the center. Okay, so this is an artist's impression that, okay, this star S2, which has a period of 16 years going around the nucleus of our galaxy. These other stars will definitely have longer periods. Okay, you just have to apply Kepler's laws and measure the distance. You'll get to know what the period is. So now imagine this is 16 years. So this was perhaps the only star which kind of gave the opportunity for astronomers to measure the whole period in their own lifetime of as a professional astronomer. Okay, for any other observation, you need to have generations of astronomers to observe these. So this S2 is the most, the most important star which has been studied. Now, I'll just mention this adaptive optics, which is extremely important, and it is a cutting edge of the technology which has resulted in this particular observation, is because we have the atmosphere which causes lot of distortion, okay, to whatever we observe. So what we see is a distorted image of the objects, and this causes inaccuracy or high error bar in observation. Okay, so if you look at it, this star Zeta Acuri, this is how they appear moment to moment, simply because the atmosphere is shifting. Now, how to go about this is that you create a laser guided star about, depending on how good your laser guide is, it can be 10 kilometers or 90 kilometers above your telescope. And this artificial star acts like your guide star. So what you're doing is that you are, while measuring, observing other stars, you're also observing this particular guide star. And this artificial star, which is a constant laser star, will go through this atmosphere, layers of atmosphere that is shifting. And then this acts like the indicator as to how your, how to correct your telescope. Okay. And then you can get a very, very high accuracy observation, high accuracy of the observation of other stars, because you have something to calibrate it out here. Okay. So this is known as adaptive optics, because every second, every moment, you are adapting to the condition of the atmosphere. And this technology was used to measure the dynamics of these stellar motions, and we were able to measure the mass of the compact object at the center of the galaxy. So you see, these were the observations which actually established the existence of a supermassive black hole at the center. Okay, and it's because of this that these three people were given the Nobel Prize, awarded the Nobel Prize in 2020. Roger Penrose for establishing theoretically the foundation of existence of black holes. Okay, Reinhard Genzel and Andrea Ghez, they were, sorry, I mean, this person is Reinhard Genzel and she's Andrea Ghez. Okay, they were given the Nobel Prize for using adaptive optics with the largest telescopes and doing these very precise observations that established the existence of our black holes. Okay, so I think I have used up my R. This is when I started, and I'll say I'm open to questions. Thank you.
Yeah, so sir, we have quite interesting questions over here. So Pramod
Yes.
Kumar is asking what happens to light after it enters a black hole?
When it enters the black hole, after entering the black hole, we have no data as to what happens to it. But as we saw in that figure, let me just go back to the figure of the trapped surface given by Penrose. So you see here, this is the light cone. At any point here, a light is emitted, it will move in this cone. Okay, it will move in only in this cone, and it remains inside this horizon. Any light here will remain in this cone. Look at, in contrast, look at the light that is emitted out here. It is in this cone. This light will move out here. Okay, it will not move in, it is outside. Look at this particular point here. A light emitted, some light will reach here, some light will reach here, some light will go here. Any light here emitted here, it will reach here, it will go here, it will go here. But any light which is emitted here, they cannot ever escape the horizon. So event horizon is the kind of final frontier for any information or light or any particle or matter or energy to come out. Okay. And the interesting thing is, if you look at this coordinate out here, this is my time axis. Okay. So this is how my time axis flows. Okay. But most importantly, if you look at the solution out here, okay, now here what happens, this particular quantity, when Rs is greater than R, okay, this is raised to -1, okay. So this particular quantity and this particular quantity, they change their characteristic when Rs moves from greater than R to less than R, okay. So what happens out here is that the space-like coordinate becomes like a time-like coordinate and it becomes unidirectional. You cannot move back in time. You cannot move back ever. So anything that falls in will fall into the singularity. That is the simplest consequence that we can think of. If you are thinking of Penrose diagrams and what happens inside Penrose diagram, and if we can have a wormhole and a parallel universe, or we can have a white hole and create a new universe, okay, these are realms of theoretical speculation, which causes very interesting, thought experiments for science fiction. But I will not talk about these because these are still speculations and we don't really have any data about these. Okay, but yes, I will urge you to, if you read about Penrose diagrams, but before Penrose diagrams, you first need to understand what is a Minkowski diagram. Okay, what is proper time and what is space-like and time-like coordinates, and we have to also understand the Schwarzschild metric and at least get some understanding of what is the Kerr metric. Okay, what do this metric geometrically signify? Then only you will be able to really appreciate what is being explained out here, how things are moving, because this is not exactly how the universe is. Okay, a lot of mathematical transformation has gone here. Okay, so this picture that we are getting out here is a coordinate transform picture. Okay, but yes, if you can form a mental picture of how the actual space looks like, then you can understand what it actually means. But understanding will require actually a series of lectures, so I will not attempt it here. Yeah, next question.
Okay, so next question is from Himanshu Lal, Yash Pratap Singh, Aniket Singh, and Alan Joe Thomas. So a similar question, like, can black holes be a gateway to another universe? And are the concept of wormholes real? And what is the end of the black hole?
Yeah, so this is precisely what I was talking about, that this Penrose diagram gives rise to these theoretical speculations. Okay, so these are mathematical constructs. Now, mathematically, things can be constructed, but whether they exist in reality or not is a very, very different thing. Because, for example, take this example of something falling into the event horizon. Okay, now if you have gone through the movie Interstellar, have you seen the movie? Okay, there what happens? They very nicely show the concept of time dilation, that as you are nearing a black hole, a person at far away distance is experiencing time dilation. So when they had a spacecraft and one guy was waiting in the spacecraft and the other guys went to a planet near the black hole. Okay, for these people, I think less than 1 hour passed, but this guy years passed. And he was just waiting for these guys to turn up, for whom only 1 hour had passed. And So that kind of scenario, which was very well shown. But what they showed in the movie was, that when they move inside and then they move back and forth in time, he moves back in time. They use the concept that the time coordinate behaves like a space coordinate and the space coordinate behaves like a time coordinate. Okay, that is why that protagonist hero, Matthew McConaughey, he was able to come back in time and, guide himself in the past. But the thing is that there are other physical aspects that happen. For example, the tidal forces. The tidal forces is differential force. If a man is falling on it, that the force on the feet and the force on the head, they will be different because of the different distance. And that tidal force will actually tear the person apart. In fact, neutral atoms will not exist. You will be only a sea of plasma when you fall in. So it is not possible for any object to preserve its shape, let alone life, as you fall inside the event horizon. Okay, so that part was completely fictitious part, but still it gave you a good idea about what can happen, what are the thought experiments that can happen when you have time travel. Okay, so if wormholes exist, wormholes are ideas which are very, very intriguing, and Penrose diagrams, they actually say that wormhole can exist, but what are the energetics of it and how they can happen? We have no idea, but maybe 500 years down the line, we might be traveling through wormholes. Who knows? They are very, very intriguing. I love to believe in fantasies, but I don't have any data to make any real comment. Yeah, next.
Yeah, so Abhinandan Angra has a question that in the time cone graph that you had shown, as one moves through the time and the points can move in space increase. So like if it's closer to the origin, the points that one can move in space are quite small, but they increase as we go ahead in time. So what does this intuitively
You
mean?
see, please understand this. You have to understand. I don't really have really time to explain Minkowski diagram. This diagram out here is existing at only one point in space-time. That is one instant. Okay, the moment I move, next instant I have to move here, and I have to draw a cone from here and like this. Okay, so what it means is that at every instant, or I can say, okay, if can I be connected to an event causally in the past? Suppose there was some event here, and I am here. Okay, can these be causally connected? Yes, because information can pass. Suppose at this particular instant, I observe two events. One is here, sorry, one is here, and the one event is here, and the other event is here. Okay, one event is here, and this event. Can these be causally connected? Yes, but this will happen only in future. And mind you, if I am moving only along this time axis, what does it mean? I'm not moving in space axis at all. So I am being stationary. So if I'm a moving person, then at next instant I'll be somewhere here, and I have to draw a cone here. Okay, I can, if I want to see the causal relation between one event here and another event here, then I have to draw this cones here and then see. Is it possible? Okay, all I can say is that from here, it is possible for me to create an event here. But it is not possible for me to create an event here. Okay, these are space-like events. But suppose there's one point here and another point here, can they be related? They can be. I have to see by drawing this light cone here and then see whether with respect to the point here, this point here, does it fall within the light cone? Okay. So whenever I am trying to find the relation between two events, whether they are causally connected or not, I have to ensure that one of the events is my origin, and then see whether the other event falls within the light cone or not. Is it clear?
Yeah, yes, sir.
Okay.
So, Mahesh wants to know about the mathematical and engineering concepts related to the study of black holes.
Engineering. Okay, engineering deals with observation. Okay, so I have dealt with two cutting edge engineering feats. One is the gravitational waves, and gravitational waves require all kinds of engineering, from vacuum technology to, you know, computation of huge amount of big data. Okay, to your electrical signals, to your material science, understanding all the material vibration that can cause noise. Very precise laser technology, very precise mirror technology. Imagine you are building mirrors which are 4 kilometers apart, and you are guiding lasers through them, and you are measuring a strain, or measuring, which is 10 raised to minus 21. So you can imagine the amount of engineering that is needed to develop these systems. Okay, so one of the reasons of why people funded the gravitational wave observation, the developing the detectors, is because they believe that, you know, these spin-off technologies from these engineering feats will definitely feed the general society. Otherwise, imagine, for 50 years, why would people spend millions and billions of dollars to develop this technology? Just because they had, they were able to market the idea, that the spin-off of these technologies, the companies that build the vacuum technology, they will be able to sell their vacuum technology for all other applications in industry and medical sciences and whatnot. Okay, so these are engineering feats which has enabled us to observe the gravitational wave. Similarly, when it comes to adaptive optics, imagine you are creating an artificial star 90 kilometers above your surface, above your you are, and in a real time you are adjusting the mirror at angstrom level of accuracy. Okay, I didn't spend too much of time on this uh, adaptive optics, but I mean, it's amazing, what you do. The next generation of adaptive optics is active optics. Okay, where you are real time, you will be changing the the reflection surface at angstrom level accuracy. So your 30-meter telescope, of which India is one of the participating countries, is an engineering marvel which we have not reached yet. When we reach there, sometimes 10, 15 years later, that is when we will say, okay, we have, a landmark has been created. We are still developing it. So if you look at adaptive optics, active optics, the technology behind gravitational wave radiation, these are all engineering feats, amazing engineering feats, which have been able to establish the theoretical paradigms which were created 100 years ago. And at that point of time, nobody thought it will ever be possible to measure such things. I hope I am able to answer.
Yes, sir.
Yeah.
And one last question from Girish. So, how far can we justify that the universe has a black hole as its center and all the matter would collapse into the black hole?
Well, we cannot actually right now, because if we believe in Big Bang, then the universe is a white hole, not a black hole. Although that concept of a white hole is also contested, but yes, what started the universe is a singularity. So a black hole has a singularity, and the reverse of a black hole is a white hole, which is also a singularity. So our Big Bang model says that we started from a singularity. Okay. But where the center is, I mean, if you don't have a boundary, can you decide on a center? This is a question that I will keep for speculative tea time discussion, not a, you know, not a formal discussion like this.
Yeah, okay, sir. So, yeah, due to time constraints, we had some questions, but now we'll have to conclude this lecture.
Yeah.
So, this session was amazing. We learned a lot of things and we feel inspired. We would always hear about black holes in news and articles, but the insight was astonishing. So the perks in observing black holes from Earth, looking at gravity as a cone of space-time, and the information about binary stars were amazing. We got to know that there's an insane amount of work behind black holes, insane amount of research gone behind these black holes. So,
Insane. It
sir,
is actually insane. Yes.
yeah. So we are very thankful to Dr. Manojendu Choudhury for spending his precious time with us.
My pleasure. Thank you.
Yes, sir. So here we conclude the event.
And I hope that everyone has liked our the first talk of arranged by DCR as well as this event. And there are some more talks there. Just follow our Insta pages and YouTube as well as the FB page as well as the our event website so that you can get more of the other competitions and other talks update. I hope you like this event. Bye.
Yeah, thank you, sir.
Okay. I hope it went well.
Yes, everything is fine. So it was too nice.